Hi all, in this tutorial we are going to have a discussion on the problems that can arise when we design the code generation phase of a compiler. So we know that a code generation phase comes after the code optimization phase and it takes input intermediate representation of the source program. Along with it will take some information from symbol table also. So this figure we discussed this in this previous tutorial also. So it's the same figure. Now, what are the issues that can occur in the design of a code generator? 1. Input to code generator. 2. Target program. 3. Memory management. 4. Instruction selection. 5. Register allocation. 6. Evaluation order. And 7. Approaches to code generation. So we will be discussing each and every point. First is input to code generator. So as I have said, the input of code generator consists of intermediate representation of source program which will be produced by the front end and together with some information in the symbol table will also be used. So what is the information that we use from symbol table? It is used to determine the runtime addresses of data objects denoted by the names in the intermediate representation. So intermediate representation will have some names of the data object. So from symbol table we will get the value of that. Then for the intermediate language we can use several choices, right? We can use postfix notation, then three address representation such as quadruple, virtual machine representation such as stack machine code, graphical representations such as syntax trees, and direct acyclic graphs are possible. So we assume that prior to code generation, the front end have scanned, parsed, and translated the source code into a detailed intermediate representation. Okay, so the value of the name appearing in the intermediate language, type checking has taken place. Okay, and type conversion operator have been inserted wherever necessary. So we are assuming that when we get the intermediate code representation to the code generation phase, these all have completed. That is substituting the values with for the names, type checking, and also type conversions has been occurred. So in this code generation phase, we assume that we can proceed without any errors. Okay. Now next is target program. So what is target program? The output of the code generator is considered as the target program. Okay, and it can take a variety of forms like absolute machine code, relocatable machine code, or assembly language. So each and every one of it has its own advantage. Okay, so first let us see what is the advantage of keeping an absolute machine language as a target program. So if we are using an absolute machine language as output, it has the advantage that it can be placed in a fixed location in memory and it can be immediately executed. Second is a relocatable machine language. Okay, so if you are using a relocatable machine language, the advantage is that it allows subprograms to be compiled separately and a set of relocatable object modules can be linked together and loaded for execution by a linking loader. Then if we are using assembly language program as output, it makes the process of code generation easier. We can generate symbolic instructions and can use the macro facilities of the assembler to help generate the code. Now next is about a stack. That is, if instruction set architecture of the target machine has a significant importance on the difficulty of constructing a good code generator. Okay, so before that stack base we will discuss this. Okay, so instruction set architecture has an important impact. Okay, So we know that reduced instruction set computer, complex instruction set computer, and stack-based architectures are available. So each of them have an impact on the target machine. So if we are using a RISC machine, it has many registers and three address instructions and simple addressing modes and relatively simple instruction set architecture. If we are using CISC machine, it has few registers, it has two address instructions, a variety of addressing modes, variable length instructions are present, several register classes will be there, and instructions with side effects will also be there. In stack-based machine, operations are done by pushing the operands into the stack and then performing the operations on operands at the top of the stack. So in our stack base, always we perform operations on top of the stack. So for achieving high performance, this top of the stack is usually kept in registers. And when we introduced Java Virtual Machines (JVM), the stack-based architectures were revived. Okay, so as we know, JVM is a software interpreter for Java bytecodes, an intermediate language produced by the Java compiler. So what is the benefit of it is that the interpreter provides software compatibility across multiple platforms. So next is memory management. Okay, so mapping of variable name to address is done both by the front-end and code generator together. Name and width are obtained from symbol table, which means the amount of storage required for that particular variable. And each three address code is translated to addresses and instructions during the code generation. And a relative addressing is done for each instruction, and all the labels should be addressed properly. So that is regarding the memory management. So next is instruction selection. So the code generator must map the intermediate representation into a code sequence that can be executed by the target machine. And the complexity of this mapping is determined by factors such as one, the level of intermediate representation. Okay, next is the nature of the instruction set architecture, and third one is the desired quality of the generated code. So if the intermediate representation is at higher level, the code generator may translate each intermediate representation statement into a sequence of machine instructions using some code templates. So the problem is that we will be translating each and every one statement into the required code. Okay, so such statement by statement code generation will produce poor code that will require further optimization. So that is a problem if the intermediate representation is of higher level. So if it is of lower level, details of the underlying machine, then the code generator can use this information to generate more efficient code sequence. Now the nature of the instruction set of the target machine also has some effect on the difficulty of instruction selection. Uniformity and completeness of the instruction set are important factors. Now, if the target program does not support each data type in a uniform manner, then each exception to general rule requires special handling. For example, in some machines, floating point operations are done using separate registers. Next, instruction speed and machine idioms are also other important factors. So, example, for each three address statement, a general code can be designed. For example, x equal to y plus z. So in order to perform this, we can use these three address statement. First, I am moving the value of y to register R0. Then I am adding the value of z with R0. So in effect, I will get y plus z. Then again, I am moving the result stored in R0 to the variable x. So these three statements are executed when I am executing this code, right? Now I have two codes, A equal to B plus C and D equal to A plus C. So if I am considering this as a single statement, I can write it using these three codes. That is move B comma R0, add C comma R0 and move R0 comma A. Similarly, if I'm using these statements only, okay, without considering this one, I have to do move r0 comma a, move a comma r0, add e comma r0, and move r0 comma d. But if I am doing it as a continuation, I can omit this statement, right? That is what it is specified here. We don't care about the efficiency of target program. Instruction selection is straightforward. For each common address statement, a general code can be designed. Now, the quality of the generated code is usually determined by its speed as well as its size. On most machines, a given intermediate representation can be implemented by many different code sequences with significant cost difference between the different implementations. Now, see, for example, if in a particular target machine I have an instruction for increment, that is, if I can write inca for a equal to a plus 1, it is an efficient target machine, right? So, if it is possible, the efficiency will increase, so speed will increase. So if inca is not possible, I have to write these three codes: move a comma r0, add #1 comma r0, and move r0 comma a. Now next is register allocation. So problem with register code generation is deciding what values to hold in what register. That is, there are a set of registers and there are a set of values, right? So we have to deal with two problems, that is what values have to go to particular register and which registers have to store particular values. So these are subdivided into two problems, okay? Register allocation and register assignment. Register allocation means during which we select the set of variables that will reside in registers at each point in a program. Okay, register allocation is set of variables that will reside in registers. Whereas register assignment is during which we pick the specific register that a variable will reside in. So register allocation, we will decide which variables has to go to which registers. And register assignment, we will pick a specific register that we can store a particular variable. So finding an optimal assignment of registers to variable is difficult even with single register machines, and it is an NP complete problem. And it becomes complicated if target machine has certain conventions on register use. For example, if we consider 8085, there are certain instructions that insist that one of the operands should be in an accumulator register. So it will create problems during writing this our 3 address codes as well as code optimization phase. Now next is choice of evaluation order. The order of evaluation can affect the efficiency of target code. Some order requires fewer registers and instructions than others. So picking the best order is also an NP complete problem which can be solved up to an extent by code optimization. How we can solve in code optimization, because in code optimization we will be rearranging the statements, right? Next, approaches to code generation. Now, the target code generated should be correct. That is the main intention of a code generation phase. The target code that we generated from this intermediate representation should be correct. And correctness depends on a number of special cases the code generator might face. Now, other design goals of a code generator are: one, it should be easily implemented, it should be easily tested, and it should be easy to maintain the code generator. So, hope you have understood this code generation phase. Thanks for watching.